Okay, so let's talk about applications of acid-base chemistry. So this is the titration section of this unit, and it's actually the lab part that we usually end the unit with. And this procedure you see is one of the things you would have been doing in class, and this is that really expensive piece of equipment. So titration is a method used to determine the concentration of a solution of acid or base. And basically we have the known concentration of our standard, and we're going to compare it to the amount of solution of our unknown concentration until indicator signals the endpoint. So it can tell us the concentration, it could help us find the unknown if given, it could be used for all kinds of things. In fact, at my dad's dairy in Platteville, they titrate every batch of milk, and it gives them information that they record for every batch of milk that goes out. So it's a very important process. It's one I wish you could actually know the physical lab skills to do it. We usually would do a formal memo with it, but we're not going to do that. So I try to give you some kind of the titration experiences through the virtual labs. I know it's not the same. I wish you could do it, but it's better than nothing. And so this is what the typical procedure would entail. And so here, this thing, if you recall, that is your ring stand. Okay. And so the thing holding this, that's your burette clamp. This is the burette, and this is a stopcock. If it's parallel like this, that means it's open and solution would drop down. If it is perpendicular, it'd be closed. And so what you would do is you put your unknown in here. That's where your unknown would go. But you would have to know how much of that unknown you put in. So let's say you put in 25 milliliters of your unknown, let's call it acid. This I would put, let's say, 1 molar in AOH, which let's say that's our base and we know the concentration of it. And we put an indicator in here. And so what you would do is you'd drop solution down, and I'll explain that in a minute. When it gets to the endpoint, what happens is we will know how much of this base was added. So then through this process, we'd figure out the milliliters of base added, and then it'll be an equation you already know to figure out the concentration of your acid. So the endpoint is the point at which the indicator changes color and stays the color after being mixed. And that can happen with like 1 drop. So at the endpoint, that solution has been neutralized. The equivalence point is the point in a titration where the number of moles of H plus ions equal the number of moles of OH minus ions. So that's actually a really important point to know. A lot of times we say the endpoint and the equivalence point are about the same, but the reality is there are some slight differences. But with the equipment and stuff that we have, it's the best assumption we can make. So this is underneath. It shows your initial solution starting to be clear. This is using phenolphthalein as the indicator, okay, for this example. That indicator is often used for a weak acid, strong base titration. And so you would titrate, and it would get a little bit pink, and then you'd swirl it and go away. You'd add a little bit of more base, swirl it, go away. And when it turns with like a half drop or a drop to this color, it's very pale, that is your endpoint. And that's where we can say the moles of acid equal the moles of base. If you go too past, then it becomes that really hot pink color. And then you probably would have to do another titration. So here is the titration procedure. So what you do is you take a measured volume of an acid solution of unknown concentration. You would choose your indicator. There's lots of places where this is online. And you want to choose an indicator where you think it probably will change. Sometimes you have kind of a good idea about this. So the example I showed was with phenolphthalein. You'll notice that indicator changes around here. Very common for a weak acid, strong base. So you want it to be a place where the equivalence point is going to be. So if we have a pH of 4 for equivalence point, maybe you choose methyl orange. Let's say you use BTV if it's closer to neutral. Maybe you use alizarin yellow if it's more basic. So you choose your indicator depending on what you're using. So measure volumes of the base of a known concentration or mix into the acid until the endpoint is reached. And you would do this dropwise. You can also use an electronic balance if you don't have your burette. And then, notice I highlighted this equation. Use MAVA equals MBVB at the end to determine the unknown concentration. Okay. And then you do have to account for multiple H's and OH's. So this is just showing a picture of all those different steps. Your starting point, slow it down as it starts getting a little more pink. That's your endpoint, that light pink, and then here it is. And I would have demonstrated for you in class, but there's a video for you to watch which will help with that. So here is an example problem. So how much 0.5 molar base is needed to neutralize 1.5 molar H2SO4? And this would be at its endpoint. So we know MAVA equals MBVB. And so I know the molarity of the acid is 1.5, but there's H2SO4. So I'm going to multiply that by 2. And you need to know a little bit more information about this. So how much 0.5 molar bases need to neutralize 1.5 molar H2SO4? Let's say I have 25 mils of it. So I have 25 mils of that acid. So I know my base is 0.5, and I'm going to solve for the volume of the base. Okay, so this ultimately ends up being a plug and chug. And I find the volume of the base to be 150 milliliters of that base that I'd have to use to just neutralize up 25 milliliters of 1.5 molar H2SO4. Now, if I change this problem to being HCl, this would be the exact same process, but instead of the 2 here, the 2 would be gone, and so that would just change your concentrations a lot. So if I didn't have that 2 there, it would make quite a difference in your amounts. So if there's no 2 here, and let's say this was HCl, your amount would be half this, of 75 milliliters. And that is if it was, let's say, HCl instead of H2SO4. So we could do the same thing on the base side. If there's more than one hydroxide, we could do the same thing. Almost always we're using sodium hydroxide for our titration problems, but you never know. So the other part of titration, so I'd want you to know the procedure and how to use this equation. The other main thing is to really understand titration curves. And so that was some of the data you could obtain from a lab. You could find the pH with each addition of your base or acid, depending on what kind you're doing. And so I do expect you to be able to look at a titration curve and know what kind of titration you have. So there is a chart in the original notes I gave you, and after looking at these different pictures, you should be able to fill out that chart. Okay, so the first thing I want you to do is notice this first titration I'm going to look at. This says a strong acid, strong base titration. What this means is the strong acid, this is going to be the flask at the bottom. Okay, so this is our unknown. So the first thing listed is going to be our unknown that we're finding out about. The second thing listed is what's going to be in the burette. And that is true for every single one of these. So if you'll notice at the bottom of our pH titration curve here, it has that, what would be in the burette at the bottom. So it's all pH versus milliliters of something. So when we look at these curves, you'll notice a strong acid, strong base on the left, and you'll notice it's a weak acid, strong base on the right. Okay, so first thing you should realize is the initial pH here. This is going to be very acidic. And so usually what we'd say is this is a low initial pH. And that's, I think, the first row. And then we have to find our equivalence point. Our equivalence point, you're going to look on this graph. You're going to find a big jump and go in the middle of the big jump. Okay. So in the middle of that big jump should have a pH of 7. And that is true for a strong acid, strong base titration. And then at the very end, it should have a high pH. It's going to be very basic. Okay. Notice the shape of the curve is kind of dramatic, how it jumps up. It's not very flowy. So that is how I would put the shape of the curve. I would actually redraw this curve. And then you would choose an indicator using that indicator chart I showed you above. And so you choose an indicator where it would change near pH is 7. Okay, so let's look at this next one. So when we compare these initial pHs, this compared to the strong acid one has a higher initial pH. Okay, it's still acidic, but it's going to be higher than the strong acid, strong base one. You'll notice there's kind of a flow to this curve. It's kind of gradual, and then it has this jump that happens later. Now this jump, the pHs can be greater than 7. It's probably like a pH 8 or 9, in fact. And then you're still going to have a high pH at the end. It's going to be very basic. Okay, and what happens is this whole region here, there's a system that happens, and it's called a buffer. We're not going to worry about buffers this year, but a buffer, basically, what happens is it's not going to change pH very easily in this range, just because what the species are in the solution. And so it makes it very, very gradual, and then it has a jump later when it can't handle it. Okay, so notice that difference in those two curves. And then again, find a good indicator that happens for that higher pH. And so like I talked about this one already with phenolphthalein. Okay, so let's look at the next two. Okay, so this one is a strong base, strong acid, and then on the right is a weak base, strong acid. So here we're going to have a very high initial pH. Okay, so it's going to be much higher than this one, than the one on the right. You notice our equivalence point. We're going to go in the middle here. Guess what? The pH is also 7. And then it's going to be very acidic at the end. And you could probably use the same indicator you would have used for the strong acid, strong base titration. Notice the shape of the curve is just a mirror image of what you had for the strong acid, strong base. So if you actually had this on an overhead or something like that, and you physically flip it, you would see it's just a mirror image. Weak base, strong acid, this is going to be a lower pH compared to the strong base. It's going to be very acidic at the end. And you'll notice its jump is going to be a little bit lower. And so its pH is actually less than 7. In fact, it's often like 4 or 5 for a weak base, strong acid titration. So its indicator is going to be different than the others. And so you can see, again, this is a mirror image of the weak acid, strong base. They're just flipped. And then the fifth type of titration I want you to know about is called a polyprotic acid versus strong base. And you'll notice there's multiple lumps here. So, oops, I didn't make a delete there. Huh? So there's multiple lumps means there's multiple H's that are coming off. So for every lump, that's an H coming off. So this one has 2 different endpoints. So it could be something like carbonic acid. It has 2 acidic H's. One that has 3 acidic H's would actually have another bump in its curve. So for polyprotic acids, I just want you to know they have this lumpy shape. They have multiple K's associated with them. And really, I just want you to know their funny shape. The indicator is a little bit harder. If you were to do a polyprotic titration, you probably would use a pH probe to gather the data rather than just doing a single thing where you'd have a color change with the endpoint, or you'd have to use something like universal indicator. Okay, so those are the different titration curves. So if I was to ask you what kind of titration that is, you should be able to answer. Or if I asked you, what is this one? Or if I asked you this one. So this first example, hopefully you'd realize is a strong base, strong acid titration. This one, hopefully you'd realize is a weak acid, strong base. And this one is a poly strong base. So that's kind of what I would hope that you would understand. Or if I said the equivalence point is greater than 7, you would identify this curve. if I say the equivalence point is 7, you could say this one, or you could say the opposite. They both have an equivalence point of 7. So in the notes, I enclosed some actual curves, just because these look a little bit nicer. So what I like is it shows that strong acid drastic curve versus that buffering region of the weak acid. Your weak base also has a buffering region, same idea, versus the strong base. So you can see them on the same curves, or the same graphs. And then here's a polyprotic acid. This is using phosphoric acid. And so it has multiple equivalence points as well. Okay. And here's another one showing kind of where the indicators change and why you would choose those different indicators, and why methyl red could work, or phenolphthalein you want to change close to where that equivalence point is. And then I really highly recommend demonstration of a titration, seeing how to actually do that. It's a very typical thing that you would do in college. So there's one more thing I want to show you, is how do you determine the Ka from a titration curve, and then show how knowing that Ka can help you determine what the acid is titrated. So this is something we would have done as a class. And so I just want to show you this method. It doesn't take very long at all. And so given a titration curve, you're going to find that equivalence point. Okay. I actually don't like this number, but we can go with this. So let's say the equivalence point for this particular curve has a pH of, let's call it 6.8. Okay, and so we're going to go down here. Let's say that is at 40 milliliters of base. So this is going to be called the method of half titration. And it's kind of a neat little trick. So what we do is we figure out what that it's at 40 milliliters, and at half, that would be 20 milliliters. Okay, so that means we're going to go to our 20 milliliter mark and go up. Okay, so at 20 milliliters, okay, we are going to say it has a pH of, I don't know, let's call it 3.2. Well, there's something really interesting that happens. So at half the equivalence point, the pH equals the pKa. Now, if you recall earlier, P means a negative log. Okay, so in this example, we're saying the pH equals the pKa, which equals 3.2. And I want to find out what the Ka is. So how we go from pH to H+, we use this equation. Well, it's going to be the same idea. Ka is going to be equal to 10 to the negative pKa. So Ka is equal to a 10 to the negative 3.2. And so you go ahead and you put that in the calculator, and that is 6.31 times 10 to the negative 4. Okay, so that would be my Ka. So there's actually charts printed with what the Ka values are for different acids. So we would go to the Ka chart, find what Ka is closest to that one, and then we'd identify that acid. So for example, if I found the Ka to be 1.8 times 10 to the minus 5, I would know that that is a Ka for acetic acid or vinegar. So that's another way that we could actually find what an unknown acid is just through this quick process of a titration. So I actually don't have a Ka chart to know my made up numbers here, but a question like this could be like an extra credit question on the exam. So hopefully this makes sense to you. You understand titrations a little bit. This is the last of the new stuff for the current unit. So let me know if you have any questions.